entitled Modeling the Mass Mortality Event in Pinna nobilis, supervised by Manuel Matias and Iris Hendricks. And so you can present the thesis, and around 20 minutes is expected to be, is what we expect from you.
Okay.
Go ahead.
Thank you. So I'm Àlex Giménez, and I will present you my master thesis, which is titled Modeling the Mass Mortality Event of Pinna nobilis, and it's supervised by Manuel Matias and Iris Hendricks. So this is the outline that I will follow. First of all, I will introduce you into the problem. After that, I will explain you the deterministic and stochastic models that we have built. Then I will discuss about how to validate our models, and finally I will show you the results and the conclusions. So, since the year 2016, a mass mortality event is affecting Pinna nobilis population, which is an endemic bivalve of the Mediterranean Sea. And basically, this mass mortality event is caused by a parasite called Haplosporodian pinnae, which is causing the disease. And we know that this parasite disperses regionally by surface currents, and the disease expression is closely related to a given temperature range and salinity range. So, in this context, we propose to study this mass mortality event from the point of view of mathematical epidemiology using the so-called compartmental models. Basically, we have our Pinna population, which are the hosts of the parasites, divided into three different states, which are susceptible, infected, and removed. And then, as these hosts are sessile animals, which mean that they cannot move, they cannot infect each other by direct contact. So there is explicit need of model the parasite population, which is this compartment here. So here we have a scheme of our model. We can see that susceptible individuals can get infected at rate beta. Then infected individuals can recover at rate alpha, and they die at rate gamma. And parasites also die at rate mu. We are going to consider that parasites only reproduce inside infected hosts, so that we are going to consider that infected hosts are like parasite factories, and they are releasing parasite continuously. Is it not clear if it is a continuous release, or is that discrete release at the end of the life of the infected host? But first of all, for the deterministic system, we are going to consider that. So, here we have our 4D deterministic system. It's the first model we built. We are considering a mean field, so big populations. And this led to this system of differential equations using standard incidence. And we have the evolution of the densities of the states. So we would like to some analytical expressions of this model, but we are only able to compute the basic reproduction number that I guess that you will be familiar with this number because of COVID. And basically, it is the number of secondary infections given by a primary infection. Using the next generation matrix method that I explained in the thesis in an appendix, we obtain this result, which is the basic reproduction number as a function of the parameters of the system and the initial condition. Okay, then we propose an approximation to this model, a reduction, to try to compute more analytical expressions. And basically, we propose a separation of time scales. We consider that the time scale evolution of the parasite is much faster than the evolution of the hosts of Pinna nobilis, so that the parasite population adjusts instantaneously to the changes on the states of the hosts. So we consider it reaches its equilibrium level instantaneously, and we have an expression of P given the states of Pinna. So with this consideration, we can build this 3D model, which is simpler, we define kappa as the ratio of mu over beta. Note that in both models, the population is constant, so the sum of the states of the Pinna is 1, because we are working with densities. And now, within this 3D model, we can compute some analytical quantities, for instance, the maximum density of infected individuals and the final density of susceptible individuals. I'm not going to show these calculations here, because they are already on the master thesis, and it's just mathematical treatment. So I will go to show the numerical results of these models. Here we can see qualitative checking of the basic reproduction number expression. Basically, we see that above the threshold, which the threshold is R0 equal to 1, above the threshold there is an epidemic, as we expect, and below the threshold there is not epidemic. We can also compare the 4D and the 3D models here, and we see that they look pretty similar qualitatively. And then another thing that we can we have to check is the approximation that we have done before, the time scale approximation. And here I'm plotting as the blue solid line. I plot the actual P, the parasite population given the 4D model, and integrating numerically the system. And then I plot also the approximation that we have here. And well, we see that the approximated P is pretty similar to the real, let's say, P. So the approximation is quite good. Okay. After that, we try to check quantitatively the threshold value. And to this end, we set R0 equals 1, which is the point. And in this way, we can isolate one of the parameters in terms of the others. And we define, in this way, the critical parameters. Then we give some values to the other parameters. And we obtain some analytical values, theoretical ones, and then we check them numerically. Here we can see that they match pretty well. And just to comment that this last plot is different because this is for the kappa parameter, which is for the 3D model, and we compute it numerically in a different way. So to finish with these two models, we have the analytical expressions for the 3D model that are shown here. And well, basically we check the analytical solution to the numerical solution, and we see that they match pretty well. Okay, after that, as there is evidence of insignificant recovery, so basically very few individuals actually recover, or none of them, we consider alpha going to 0. So this leads to a much simpler system, which is basically an SIR with a saturation term. And this leads to much more beautiful expressions, analytical expressions like these ones, and that we can, again, check it numerically. And well, they match perfectly, the analytical and the numerical solutions. So now we finish with the deterministic models, and we go to the stochastic model. So the models that I have shown before were for big populations with small fluctuations, but now we are going, well, I mean, there are a lot of small populations of Pinna nobilis, so we need to take into account the fluctuations, and we built a stochastic model given this master general model. So the first thing that we can do to check this master equation analytically is to perform a mean field approximation, and we see that we recover the 4D deterministic model that we had, so this is good. And then we check this model numerically. As I've said at the beginning, it is not clear if the release of parasite from infected hosts is continuous or just at the end of their life. So here I'm going to compare the discrete parasite production with the continuous one. That is what I have considered in the deterministic model. So first of all, I set the system in its mean field limit. So I choose a population of 1 million individuals. This is a plot. Well, these two plots are for a single run. And then we can see that fluctuations are really small, as it is expected. And qualitatively comparing these two plots, we see that both discrete parasite production and continuous parasite production led to the same results. But we can also compare this quantitatively. So I take some averages over 100 realizations. And well, we see that basically the numbers are the same, and they match within errors, and the relative error is really small. Then we can also compare this with the deterministic system that it should approach, and we see that it is approaching the deterministic system. So, okay. Then we go to the small population, which is of more interest. We go here, I simulate the system for 100 individuals, and I take averages over 10,000 realizations. So qualitatively, we see that the two plots, the two situations are similar also. But we can see here in the values that they are a little bit different, but however, they match within errors again. So we can conclude that both situations led to the same results, the continuous and the discrete parasite production. So now I'm going to discuss how to validate these models. Our idea is to have some experimental values, these ones, and just to fit one parameter. For instance, the infection rate. We choose this parameter to fit because it is very difficult to obtain experimentally, but the reality is that we don't have a lot of data, so we don't have these experimental values. Then in this situation, we propose a further model reduction due to this lack of data. Basically, we set alpha equals to 0 as the last 3D model. And we are going to do this crucial consideration, which is that kappa is bigger than S. This is supported by a paper that I cite in the thesis. And then this allows us to go to this reduced model, which is an original SIR model, where this beta prime is an effective infection rate, which is interesting because it's given by the product of beta, the real infection rate, to the ratio of lambda, the production rate, to mu, the death rate of the parasite. So it makes sense. Then, to try to fit this model, we have only two parameters and an initial condition. So we are going to consider one of the parameters, the death rate, as 1 month to -1. This can be obtained by visual inspection of the data, and it also, the biologists working in the field agree with this value. And then we just need to fit beta prime and the initial condition. So we take experimental data from this paper of Garcia Mark that I'm going to explain how is the data. They collect Pinna nobilis individuals from some places like Portugal in Catalonia, and they placed it in several water tanks. Okay, then they can keep track of the survivorship of the Pinna nobilis, so we can get track of the R compartment, so we know at every time step, let's say, how many dead individuals there are. The resolution of the data is a monthly resolution, and the thing is that the temperature should be constant, these water tanks, but when the animals started dying, they decreased temperature in order to try to save them. So there is only 2 water tanks with approximately constant temperature, and these ones is the ones we are going to use. So here we have the fittings. To fit, the circles are real, is the real data, and the line is the fitted line. I'm going to explain how I fit this line. Basically, I use optimization of the mean squared error. So I run several simulations with several combination of parameters, and I choose the one that minimizes the mean squared error. So here are shown the optimal values, and these heat maps are nothing but the minimization of the mean squared error. We see that there are some values that minimize better the error than others, but these ones are the optimal, the absolute optimal. So, well, here we can see that the important thing of this fitting is that we see that for increasing temperatures, we have an increasing value of the infection rate, which is expected because we know that the disease expression is higher for higher temperatures. Okay, then ideally, we would like to go back and fit the 3D and 4D models, but, well, because we know this relation, but as we don't know any of these values experimentally, obviously we get a linear dependence here, and we have a lot of combinations that fit in the same way the model. So here I show an example that all these values that give rise to the same beta prime fit in the same way the model. And finally, we would like to fit the 4D model, but the same happens with more degrees of freedom. So just I'm showing a particular set of the parameters that can reproduce the data, but I mean, there are a lot of choices. So the ongoing work, our final idea would be to build a metapopulation model, which basically is to consider several populations distributed in the Mediterranean Sea, and let the parasite to reach the populations using the currents, the surface currents, and we would run in each of the populations our models. Okay. And finally, to conclude with, we can say that we have built deterministic models, and we are being able to find analytical expressions to these models. Then we have also built a stochastic model, which approaches the deterministic model in the mean field limit, as it should be. Despite the lack of data, we are able to somehow fit our model. And well, as ongoing work, we should include parasite mobility with surface currents integrated in a metapopulation model. And that's all. Thank you for your attention, and I hope you have enjoyed.
Thank you, Àlex. So we will stop now the recording and continue with the questions.
Okay.